Alright, I wanted to make another video here looking at Laplace transforms here. I wanted to look at a more complicated problem where you could use a Laplace transform. So here I want to look at an example where we have an oscillating input concentration. This is not such a crazy scenario. If you're looking at something like a wastewater source, it's possible that the pollution level or the flow, but here we're just going to look at concentration, could go up and down throughout the day. So we might have like a Cn versus T that looks kind of like, looks something like this. So this isn't so crazy. Pollution comes in at one part of the day and then it decreases as people go through their normal routine. And so let's imagine that we have this Cn coming in with the flow into a reactor, and then we have some C out that we would like to be able to figure out, and it's well mixed tank. So in this situation then, yeah, we'll also assume that the initial concentration is 0. It has some volume V, and then it's going to have some characteristic time that's going to be Q over V. We're going to use that variable. And so then my Cn function here will say is equal to, it's going to be a time variable input, and I'm going to use C0 over 2 times 1 plus sine of omega t. So omega would be the frequency. The bigger omega gets, the closer together this wave is, the more it's oscillating. And this will bounce between C0 and 0. C0 up here at the top and down to 0. So to do this, we're going to need to first set up a mass balance. And so that's going to be like our other ones, dc out by dt equals q times Cn minus q times C out. And if I divide by v and I plug in my function there for Cn, I'm going to get, I'm just going to write it kind of over here, dCn by dt plus 1 over tau q over v times C out is equal to 1 over tau times C0 over 2, 1 plus sine of omega times t. Okay, well, the omega t will always be inside the sine whenever I write this out. So we can do this with Laplace transforms. So if I take the Laplace transform of this guy, imagine I'm Laplacing the whole thing, I'm going to get S times Cn bar minus my initial condition, which is 0, so it's just a 0, plus 1 over tau times C out bar. Again, I'm using bar here to refer to the version of this dependent variable here in the frequency domain. And that's equal to C0 over 2 tau times the Laplace transform of 1, which is a 1 over S, plus the Laplace transform of sine omega t, which if I go and look that up in my table here, sine of AT is A over S squared plus A squared, so that means we just get omega over S squared plus omega squared. All right, so that's all in the Laplace domain now. And so then I can, oh, this is supposed to be C out over here. So now I can solve for C out in the Laplace domain, C out bar, if I basically factor out the S plus 1 over t and move it over, C0 over 2 tau times 1 over S times S plus 1 over tau plus omega over S squared plus omega squared times S plus 1 over tau. Okay, and so this thing I can't easily invert. Maybe you could find a table that gives you the value, but I wanted to go ahead and do it using partial fraction decomposition. So I'll just kind of write out that we're going to do this part over here. So omega over s squared plus omega squared times s plus 1 over tau. And I'm going to need some function, something up here, a over s plus 1 over tau plus bs plus d. A, b, and d here are just some things that I have to determine, constants here. S squared plus omega squared. I would use c, but I've already used c, so to try to make it less confusing. So I got to break it apart, and I need to find the values of a, b, and d that when I cross multiply and add those together give me omega. So if I just do the cross multiplication, I'm going to get as squared plus a omega squared, and then this one is going to be plus a b s squared plus ds plus bs over tau plus d over tau. Okay, those are my 6 terms, and I need all those. I need to find values of a, b, and d that will give me just an omega. And so basically I can group them together here into ones that have no s, one that have an s, and one that have an s squared. So we have a omega squared here. I'm going to underline them as I use them, plus a d over tau. Those don't have any s, so those need to add up to my omega. Then for the s terms, we have a ds term here and a bs. We have ds plus bs over tau needs to equal to 0. And then that takes care of those two, and then my s squared terms. So as squared plus bs squared has to be 0. And we know that s isn't 0, so that, or s squared can cancel out of that one, and s can cancel out of that one. And then we have 3 equations and 3 unknowns, so we can use it to find a and d. So I think the easiest way to do this is an a and d, so this is the one I'm going to go to last. And so I can take this one. This will be pretty easy to put together. So this is going to give me a is equal to negative b, or b is equal to negative a. So I can go back and plug that one in over here, and then I'll have an a and a d that I can solve those two. So we get a d plus a negative as over tau is equal to 0. Oh, not s, a over tau. So the s's go away. And so therefore d is equal to a over tau. Okay, so I have a is negative b, or b is negative a. Then I have d is a over tau, and I can plug that one in over here. So a omega squared plus a over tau squared has to give me omega. Therefore, a is going to have to be equal to, if I multiply by tau squared here, then I'm going to get omega times tau squared on that side, and then I can factor out. I get a 1 plus omega squared times tau squared. Okay, so that's a, and we're done with that one. And then d is a over tau, so that means that d has got to be equal to omega times tau. I lose this 1 squared term, and I keep the denominator. And then b is going to have to be negative omega tau squared over 1 plus omega squared times tau squared. Okay. So from there, Now I've done my partial fraction decomposition. I can go back to my equation here and rewrite this in a form that's a little bit more workable. I'm going to need lots of space, so I'm going to write this over here on the far left side. C out is equal to C0 over 2 tau times 1 over S times S plus 1 over tau. So I didn't do anything with that part. But then here I've gotten so plus my A term is omega tau squared over 1 plus omega squared tau squared. All of that, and A is 1 over S plus 1 over tau in my decomposition. So again, these are all constant. That's why I'm writing it that way. That way I just can focus on the inversion of these pieces. So that's A, and then I have the BS over that S squared plus omega squared term. So that's going to be a minus omega tau squared over 1 plus omega squared times tau squared times S over S squared plus omega squared. Okay, and then the last one is the D term, which we said is plus omega tau over 1 plus omega squared times tau squared. And that was my D over S squared plus omega squared. Oh, sorry, that was 1 over, it'll be a 1 over S squared plus omega squared. Okay, so that's my partial fraction decomposition. I broke it into these 3 pieces. So now I need to invert this thing, I need to invert this thing, and that thing, and then I need to pull the constants through and clean up clean it up a little bit. So C bar out, this will just come right on through. And then my first term here, if I go to my table of integrals, I have a table here that has most of the ones I want. There's one that's not in that table, and it's this transform e to the at minus e to the bt over a minus b is 1 over s minus a, s minus b. So if a is 0 and ours and the other one is minus 1 over tau, I can transform it back to this guy. So I get e to the 0t minus e to the minus t over tau divided by a minus b, so that's a 0 minus negative 1 over tau. So that's the first one. And then we have the second term here, so I've got to bring all the constants through. Omega tau squared 1 plus omega squared tau squared. This one, 1 over s plus, that is just my exponential here, so e to the minus t over tau. And then we have a minus omega tau squared over 1 plus omega squared times tau squared. And then s over s squared plus omega squared, if we go to our table, s over s squared plus omega squared is cosine of at. So cosine of omega t here. Our a is an omega. And then the last one, omega tau over 1 plus omega squared tau squared. And here actually I'm going to mark out that tau. I would leave this tau over here, or sorry, this, not the tau, the omega. If I want to leave that omega over there, and if you look at the identities, there's one that works for that. So sine of at is a over s squared plus a squared. So omega goes right in, and this just becomes sine of omega t. Okay. And so, yeah, we've got a tau there. So now we've done the inversion, and then if I wanted to clean that up just a little bit, maybe for c out of t, let's see, I'm going to leave c0 over 2 there. Here I've got, this is a plus a 1 over tau, so that's going to go up to the numerator of both of those. And then when I divide, so I'm going to divide this tau all the way through. Basically, it's just going to cancel out, leave me a 1 for that term. And then for this term, it's going to leave me a minus e to the negative t over tau. That tau is going to cancel there. And then over here, it'll get rid of the first, that tau, omega over 1 plus omega squared tau squared e to the minus t over tau. For this one, it leaves me with an omega tau over 1 plus omega squared tau squared cosine of omega t. And then the last one, the tau cancels out, 1 over 1 plus omega squared tau squared times sine of omega t. So there it is. We've done the inversion, and so this is going to be, this big long function is going to give me the output for this oscillating input function. And so we would expect this, our input function's looking like this, and we would kind of expect, because it's a well-mixed tank, that when it comes in there, it's also going to probably oscillate around some, but it's going to dampen out the peak. And so it's got to start, so this is in, and then see how it's going to like kind of go up, and it should get kind of dampened out by mixing. If you mix it up, that should presumably knock that down. And so I put together a little spreadsheet to look at this, and I put in values here. So spreadsheet with, I put in C0 is 100 milligrams per liter, omega is 1 minute to the negative 1, and V is 1 meter cubed, and Q is 0.1 meters cubed per minute, which gives me a tau value of 10, and then I can play around with that. And so I'll just quickly turn on the display. Okay, so here's an example of that output. So you see the input oscillating up and down, and then the output here is also oscillating, but it ultimately dampens out these peaks a lot. So one way that you could get rid of peaks if they were coming into a process, like these peaks could be bad for a treatment process. This would dampen those down if you have enough mixing. You could change the values. So if you made a Q, let's say we made it like a 5, quite a bit bigger, then it would, that's going to slow this down. It's going to make the oscillations even smaller. Let me put it back. 1. And we could make the oscillations happen more quickly here, which now everything is really moving around, but you see it starts getting closer to just a regular exponential constant input as that frequency goes up more. If you take the frequency down, on the other hand, then yeah, it starts to really still oscillate quite a bit. So anyway, that is the how you can do a Laplace transform for a more complicated input function. You could solve this other ways, but this is how you would do it with Laplace transforms.